9.5 is the last section in Chapter 9. We're still performing hypothesis tests on two samples. Only in this section, we were comparing the variations of the two samples rather than the means or the proportions. In our first example here, we have two samples of quarters. Some were made before 1964, some were made after. We're looking at their weights and more specifically, the variation of these weights. A lot of times it'll give you the mean along with the standard deviations, but for these problems, we only care about the standard deviations, and this important information is organized in this table here. We have our pre-1964 quarters and their standard deviation, and the same thing for the post-1964 quarters. Just like every other hypothesis test we've done, our first order of business is to write these hypotheses. And when we write them, we're writing them about the variances of the samples. Variance is the standard deviation squared. Symbol for standard deviation is sigma, and we're just going to attach a squared on it. We want one of these for a pre-1964 quarter and another one for a post-1964 quarter, making our null hypothesis the fact that these two are equal. They have the same standard deviation. And the alternative is that they're not equal. They're not the same. When we actually perform this test, if you think back to the previous chapter, when we did one sample tests about variance, we used a chi-square distribution. It's going to change for two sample tests. We're going to use a new distribution called the F distribution. Test statistic for these problems is given by this equation. F equals the variance of the first sample, which is the standard deviation squared, divided by the variance of the second sample. Again, standard deviation squared. When we decide which sample is the first and which sample is the second, it is important and it does matter. S1 is always going to be the larger standard deviation. So the larger one has to go on top. The smaller one's on the bottom. F is always going to be greater than 1. So when we look at these two samples here, we have this sample is larger than that sample standard deviation, which means that this is S1, and then this is S2. All right, so with that in mind, we have a sample size of 40 for both of these, so that doesn't change. When we plug it in, we square each of those standard deviations, divide the two of them, and we get a test statistic of 1.973. Finding the critical value, here we're going to use our new distribution called the F distribution. The shape of this is the same as a chi-square distribution. It's skewed to the right, unlike the normal distribution or the T distribution. When it comes to testing our hypotheses, our null hypothesis was that these two samples have the same standard deviation. Alternative was that they're different. That means we have a two-tailed test. Okay, it told us that the alpha was 5%, but we don't care about that whole alpha. These tests are only right-tailed and always right-tailed. So we really only care about that right tail of the test, meaning we're really working with an alpha of 0.025. This information is coming from the information it gave us in the tables. Remember, this was S1 because that standard deviation was bigger. Degrees of freedom found the same way as always, n-1. And now we're going to go to the actual F distribution table. So there's a couple things we have to look at here. First of all, there's a lot of different tables here, okay, and it changes based on the alpha level. So first off, we're looking at an alpha level of 0.025. There's an entire different page for an alpha level of 5%, 1%, etc. Okay, this top part is for our first sample. Degrees of freedom is 39. We're going to go to the closest thing that we have, which is 40. Second sample, degrees of freedom of the denominator. Again, the closest thing to degrees of freedom of 39 is 40, and we're just going to find where these two intersect. And they intersect at 1.88, so that's our critical value. So here we have everything compiled. We have our hypotheses, we have our critical value, 1.88, and we have our test statistic, 1.973. Now we want to draw the curve. So our curve looks like this. This is our critical value here. And if we were to actually put this test statistic on that curve, it would be just to the right of that, right there. That's in the shaded region. Now we're going to make our decision the same way we always did. Reject the null hypothesis since the test statistic falls in the shaded region. And when we write our conclusion, it's still always about that alternative hypothesis. There's sufficient evidence to suggest that the standard deviations for pre-1964 and post-1964 quarters are not the same. These can be a bit tricky, so let's do one more example. In this example, we have data on New York Times bestsellers. We have a sample of 25 fiction books, and the standard deviation for the amount of time they spent on the bestseller list was 6.17 weeks. We have another sample of 15 nonfiction books. They have a standard deviation of 13.12. The actual question is asking, at an alpha level of 10%, can we conclude that there's more variation in books on the nonfiction list? Hypotheses always start off the same way. We're saying that these two standard deviations, or variances in this case, are equal. We always write these about the variance, even if we're talking about standard deviation. So standard deviation is sigma, variance is sigma squared. Alternative hypothesis is saying that there's more variation in the nonfiction books. So that's why we have a greater than sign here compared to a not equal to on the last problem. Part B, find the test statistic. Remember, we're dividing these variances, but we're making sure that we have the larger one on top. So with that said, this one is larger, so our S1 is based on that sample. It's a sample size of 15, standard deviation of 13.12. The smaller one goes on the bottom, sample size of 25, standard deviation of 6.17. At this point, we just plug it in, square the top, square the bottom, divide them, 4.522 as our test statistic. Critical value. Again, we're working with a distribution that's skewed to the right, and it told us that the alpha level was 10%. We're not going to cut that in half this time. The reason we cut it in half on the previous example was that the alternative hypothesis was not equal to. It was split across the right and left side. This time our alternative hypothesis was greater than, so all of that alpha goes on the right side. We talked about which sample went on top. It was the sample that had 15 as the sample size, and that gives us degrees of freedom of 14. Second sample at a sample size of 25, degrees of freedom is 24. Now we jump to our table, and we're going to look at the intersection of those two values. So closest thing to 14 is still this one right here. And then we had 24 for our second degrees of freedom. That's this one over here. We're going to go over until they intersect, and they intersect at 1.78. Also, just as a note, I'm on the page that says our alpha level is 10%. So our critical value, 1.78. Lastly, we want to draw out this curve. We have our critical value of 1.78. We found the test statistic previously. It was 4.522. We would put that on the curve. It's way out in the tail here. That's in the shaded region, and we're using that justification to reject the null hypothesis. Writing our conclusion, it's always about our alternative hypothesis. And in this case, there's sufficient evidence to suggest that the variance of books on the nonfiction list is greater than the variance of those on the fiction list.